Welcome to video number 23 about how to make a chess program in Go. This time we will handle a problem that we had from beginning. The one who makes the move when we reach the leaf of the tree, the one who is to move can do any capture he or she wants. And that makes the evaluation to be completely out of order, and the moves in the end will be very strange to avoid this. We will deal with this. The function that we will use is called quiescence. I say quiescence, but I heard people say quiescence, so I will say QS to avoid future embarrassment. Okay, the QS function could be, I would say, the same as the search function, but only with captures. So when we make the evaluation, it's always a quiet position. It could be an ordinary alpha beta function, recursive, the same as search. It will work perfectly well. The only problem with this is that the search tree can explode because there can be lines with a lot of captures, but that's not the normal case. The normal case is that every capture reduces the number of moves left, and suddenly, after a while there are no more captures to do. That's the normal QS function. We will do it in a little bit different way. Another function is the one that we will start with here, the C function. And that is the static exchange evaluation. So what this function is doing is it uses only 1, 2 square and see without making any moves. Try to see how the exchanges will end up. This function is a little bit complicated, so I had to prepare and write it in beforehand. The idea is from many years ago, from Tord Romstad, the godfather of chess programming. The C function starts with receiving a from and a first move, and a from and 2 square, and it's the 2 square that we will evaluate. We start with a bit board with all the pieces on the board, and we clear the bit with the from square, because there might be pieces extraying the from square to the 2 square. After that, we create a bit board with all the attacking pieces, white and black, to the 2 square, taking into account that the from square that the piece is removed, so we can X-ray. We do the same little trick that we use when we try to find out if the king is in check. We imagine the rook at the 2 square, and we see if it hits a rook or a queen. Then we know that a rook or a queen is threatening the 2 square. We end with the occupancies bit board, all the pieces, but in this case the from piece is removed, the first from piece. Now we check if the other side have any attackers. If not, it's time to stop the search. Now we will loop through all the attackers for each side and keep track of the material gain and loss for each capture. And we will remove every from piece, from square, from the OCC bitboard to explore new X-rays through that square and find new attackers. We save the last attacking or capturing piece value because we will use that later on. The capture list array there is used to keep track of gain and losses. We change side for every loop, and the first thing we do in every loop is to find out the least valuable attacker, because there is no reason to capture with the queen if we can do the same capture with the pawn. And now we again remove the piece that capturing from the attacker's bit board. We use this little trick to remove the bit from the attackers from square. Because of that, we can have new X-ray attacks through the removed square, removed bit, and we try out the new X-rays with sliding pieces. Of course, only sliding pieces are used here. And now we can add in the last attack value from above that we saved to use here, and we make a kind of minimax function here. And below we save a new piece value in the last attack val. The last attack val here will be saved again below to be used in the next loop. If the king captures, then this is the last thing we will do. Actually, something is wrong here. First of all, let's change the comment. First I thought I could use 10,000 here, but why not use the piece value of the king? We need the absolute value of the king value. It should look like this, but this is way too complicated. Can do it much easier to just use the value of the white king. If there are no more attackers, we can just break the loop. And finally, we can go through the capture list array and find out the optimal sequence of move for both white and black, and return that value. And now we will actually make the code for the QS function. It's much simpler than the C function. So the QS function I will do here is, the only thing it's doing is go through all the captures in the position and evaluate them together with the C function. There is a risk with that, of course, because the C function doesn't find everything, and the QS will not find everything either. Maybe, I just say maybe, a better way is to make the QS function recursive in a normal alpha beta way, but only with captures, and at least a couple of recursions before going into this type of QS that I do here. But only test can show which one is the best. Okay, so we need the QS, and we only use beta because it's not recursive. We don't need alpha here. And we send in the bitboard, not the bitboard, the board, and we return an int. We can call the evaluation for EV here, and we need to have the sign according to who is to move. And if evaluation is above beta or equal, well, we are good and we don't need to do more. We don't need to try captures that are bad for us. So we just return the value. Otherwise, we go on, and the best score we have for now is the evaluation. So let's call the move list with captures for QS list. So, and we should initialize our QS list, and we need to send in the board. And let's write that function init QS, and we need the move list, the QS list, and the board. So what will we do here? We just clear the move list and generate captures. That's all, I think. Yeah, all captures, move list, and that's that. Init QS. We will have this bitboard. That bitboard we will use. We will keep track of two squares. The squares we are evaluating, because we want to evaluate 1, 2 square only once, not 2 times. So bitboard 0 to start with, and let's go through all the capture moves, and that is the QS list, and we can dig out the from and to square. So if it's done, if 2 square is done, then we continue. Don't do the same 2 square twice. And then we continue. In fact, this works because we pick the lower value pieces first, and we don't need to check the others to the same 2 square. Okay, so set done to set the bit to 1. It's done. And run the C function, get the value. If C is less than 0, we are not interested, we just continue with the next capture. We are not interested in equal captures, so maybe we should set the equal here. If the C value is 0 and the capture is empty, is not a capture move, then it has to be, actually it has to be a promotion, and it's a promotion that didn't capture or was not captured. So we need to set this C value by hand, because C doesn't fix that. C doesn't handle promotions without capture. So, and the score is our evaluation plus C, and if it's bigger than best score, set the new best score. If score is more than beta or equal, then it's a cutoff. So we can return the score. And we need to return the best score in the end. I need to change one thing here. This one should be before, so we can use the equal sign here, of course. Okay. Until next time, bye bye.